Welcome to this scientific lecture on ferrofluidic droplets and their role in electrodynamic energy harvesting applications. Today we'll explore the fascinating intersection of fluid dynamics, magnetism, and energy conversion. Let's begin by understanding what ferrofluids actually are. Ferrofluids are colloidal suspensions containing magnetic nanoparticles, typically magnetite or iron oxide, dispersed in a carrier liquid such as oil or water. These particles are incredibly small, on the order of 10 nanometers in diameter. They're stabilized by surfactant molecules that prevent aggregation due to van der Waals forces and magnetic dipole interactions. Here we see a ferrofluid droplet. The red dots represent magnetic nanoparticles suspended in the carrier fluid. When we apply an external magnetic field, these particles align and the fluid responds dramatically. The key property is superparamagnetic behavior. At room temperature, individual nanoparticles exhibit no permanent magnetization, but they rapidly magnetize when exposed to an external field. Before diving into energy harvesting, let's review the fundamental principle that makes this possible: electromagnetic induction. Let me pose a question. What is Faraday's law of induction, and why is it central to energy harvesting? The answer lies in this equation. The induced electromotive force epsilon equals negative n times the time derivative of magnetic flux phi b. This tells us that the induced voltage in a coil is proportional to the rate of change of magnetic flux through that coil. The faster the flux changes, the greater the voltage generated. Where magnetic flux phi b is the surface integral of the magnetic field B dot, the area element dA. Now let's examine solenoids and coils, which serve as the electromagnetic transducers in our harvesting system. A solenoid is a tightly wound helical coil of wire. When current flows through it, it produces a nearly uniform magnetic field inside the coil. The magnetic field inside an ideal solenoid is given by B equals mu0 times N times I, where mu0 is the permeability of free space, N is the turn density, and I is the current. This diagram shows a solenoid with multiple windings. The green circles represent the coil turns, and the red arrow shows the magnetic field direction. A ferrofluid droplet inside experiences this field. Notice that the induced voltage depends linearly on the number of turns N. More turns means more voltage for the same flux change rate. Let's now discuss the dynamics of ferrofluidic droplets in oscillating systems, which is crucial for energy harvesting. You might ask, why use ferrofluids instead of traditional solid permanent magnets for energy harvesting? The answer involves several unique advantages that ferrofluids offer over solid magnets. First, ferrofluid droplets can conform to complex geometries. They're liquid, so they can fit into spaces where solid magnets cannot. Second, their magnetic properties are tunable. We can adjust the concentration of nanoparticles to optimize performance for specific applications. Third, being liquid, ferrofluids exhibit lower mechanical wear and reduced friction compared to solid magnets sliding in tubes or channels. Fourth, they provide enhanced damping characteristics, which is valuable for controlling resonance in oscillating systems. Now let's explore the actual energy harvesting mechanism in detail. Here's a schematic of a typical ferrofluid-based energy harvester. The brown sphere is the ferrofluid droplet inside a cylindrical channel. Green circles represent coil windings at top and bottom. When the device experiences mechanical oscillations, perhaps from vibrations or human motion, the ferrofluid droplet moves up and down through the coils. As the magnetized droplet moves, it changes the magnetic flux threading through the coil windings. The average power harvested is given by 1 over T times the integral from 0 to T of V squared of T divided by RL dt, where V is the induced voltage and RL is the load resistance. A critical aspect of energy harvesting is resonance and frequency optimization. The ferrofluid droplet system behaves as a damped harmonic oscillator with both mechanical and magnetic damping components. The equation of motion is m times x double dot plus c times x dot plus k, x equals f0 times cosine of omega t, where m is the effective mass, c is the damping coefficient, and k is the spring constant. Here's an important question. What is the optimal operating frequency for maximum power output? The optimal frequency omega opt equals the square root of omega 0 squared minus c squared over 2 meters squared, where omega 0 is the natural frequency. Maximum power transfer occurs when the excitation frequency is near the system's resonance frequency. This is where amplitude is greatest. Let's discuss some practical design considerations for ferrofluidic energy harvesters. First, coil geometry matters significantly. There's an optimal length to diameter ratio that maximizes flux linkage while minimizing resistance. Second, wire gauge selection requires balancing electrical resistance against the number of turns we can fit in available space. Third, ferrofluid volume represents a trade-off. Larger volumes provide stronger magnetic fields but increase inertia, potentially reducing responsiveness. The conversion efficiency ETA equals piezoelectric divided by P mechanical, which equals V squared over RL divided by F 0 times versus average. Typical conversion efficiencies for small-scale ferrofluidic energy harvesters range from 5 to 20%, depending on operating conditions and design optimization. Now let's explore real-world applications where ferrofluidic energy harvesting shows promise. Application 1 is wearable electronics and health monitoring devices. These harvesters can convert body motion into electrical energy to power sensors. Application 2 is wireless sensor networks and civil infrastructure. Bridge vibrations and building oscillations can power autonomous monitoring systems. Application 3 is ocean wave energy conversion. The oscillatory motion of waves provides an ideal excitation source for ferrofluidic harvesters. This illustration shows a wave energy harvester. As waves oscillate the structure up and down, the ferrofluid droplet moves through coils, generating electrical power continuously. Application 4 is automotive suspension systems, where vehicle vibrations during driving can be harvested to power auxiliary electronics or sensors. Let's touch on some advanced topics, specifically magnetohydrodynamic effects in ferrofluidic systems. An important question: how does the carrier fluid's viscosity affect harvester performance? Higher viscosity increases damping, which reduces peak oscillation amplitude. This decreases power output at resonance but can broaden the effective frequency bandwidth. The drag force on a spherical droplet follows Stokes' law. F drag equals 6 pi times eta times r times v, where eta is dynamic viscosity, r is droplet radius, and v is velocity. At high velocities, Kelvin-Helmholtz instability can occur at the ferrofluid carrier fluid interface, causing droplet breakup and performance degradation. Surface tension plays a crucial role in maintaining droplet integrity. The balance between magnetic forces and surface tension determines droplet shape and behavior. Let's discuss optimization strategies for maximizing energy harvesting performance. First, optimize magnetic properties by carefully selecting nanoparticle composition. Cobalt ferrite offers higher magnetization than magnetite, for example. Second, implement impedance matching between the coil and electrical load. Maximum power transfer occurs when load impedance equals source impedance. The optimal load resistance RL opt equals the square root of R coil squared plus omega L squared, where L is coil inductance. Third, tune the natural frequency through geometric design parameters like channel length and droplet mass to match expected excitation frequencies. Fourth, consider multi-droplet configurations with different resonant frequencies to harvest energy across a broader frequency spectrum. Now let's examine current challenges and ongoing research directions in this field. Challenge 1 is long-term stability. Over time, nanoparticles may aggregate despite surfactants, degrading magnetic properties and fluidity. Challenge 2 is temperature sensitivity. Both viscosity and magnetic properties vary with temperature, affecting performance across environmental conditions. Challenge 3 involves scaling effects. Behavior at microscale differs significantly from macroscale due to surface forces dominating over volume forces. One promising research direction is ionic liquid-based ferrofluids, which offer improved stability and wider temperature operating ranges. Another direction is exploring magneto-rheological coupling effects, where applied magnetic fields dynamically alter fluid rheology for adaptive damping. Let's compare ferrofluidic harvesters with other electromagnetic energy harvesting technologies. Solid permanent magnet harvesters typically achieve higher efficiencies, around 30 to 40%, but suffer from mechanical wear and friction losses. Piezoelectric harvesters excel at high-frequency applications but are rigid and can be brittle, limiting their use in certain environments. The ferrofluidic approach offers unique advantages in flexibility, durability, and the ability to harvest from multi-directional or chaotic motion. Let's take a deeper look at the mathematical modeling of ferrofluidic energy harvesters. The magnetization vector m equals chi times the magnetic field intensity h, where chi is the magnetic susceptibility of the ferrofluid. For ferrofluids, the magnetization follows the Langevin function, accounting for thermal fluctuations of nanoparticle magnetic moments. M equals ms times the quantity cotangent hyperbolic of alpha minus 1 over alpha, where alpha depends on particle size and field strength. To accurately predict harvester performance, we must solve coupled electromechanical equations that include mechanical motion, magnetic field dynamics, and electrical circuit behavior. The induced voltage V of t equals negative n times the time derivative of mu0 times m of x times a, explicitly showing the dependence on droplet position x. As we conclude, let's look at future prospects and emerging technologies in this field. Hybrid systems that combine ferrofluidic harvesters with piezoelectric or triboelectric elements show promise for enhanced power density and broader frequency response. Smart ferrofluids with stimuli-responsive properties could enable self-tuning harvesters that automatically adapt to changing environmental conditions. Integration with advanced energy storage, such as supercapacitors or thin-film batteries, enables self-powered autonomous systems with minimal maintenance. Miniaturization efforts aim to create micro-electromechanical systems, or MEMS-scale ferrofluidic harvesters, for powering implantable medical devices and microsensors. Artificial intelligence and machine learning algorithms are being developed for predictive optimization, analyzing vibration patterns to maximize energy extraction in real time. Let me summarize the key concepts we've covered in this lecture. Ferrofluids offer unique advantages, including conformability, tunability, and reduced mechanical wear compared to solid magnet systems. The fundamental mechanism is electromagnetic induction governed by Faraday's law, converting mechanical oscillations into electrical energy. Resonance matching between excitation frequency and system natural frequency is crucial for achieving optimal power output. Applications span a wide range from wearable electronics to large-scale ocean wave energy conversion systems. Current challenges include long-term stability, temperature sensitivity, and understanding scaling effects from micro to macro systems. The future lies in hybrid systems, combining multiple transduction mechanisms and AI-driven optimization for adaptive performance. In conclusion, ferrofluidic droplet-based energy harvesting represents a fascinating intersection of fluid mechanics, electromagnetism, and sustainable energy technology. The field continues to evolve with advances in nanomaterials, modeling capabilities, and manufacturing techniques. As we push toward more autonomous and self-powered systems, ferrofluidic harvesters will likely play an increasingly important role in powering the sensors and devices of tomorrow. Thank you for your attention, and I encourage you to explore this exciting area of research further.